All right, today we're going to cover the last section of Chapter 12, the last section of Calc 3, and it's titled Arc Length and Curvature. And I'd like for you to remember that we've actually talked about arc length once before. We did it when we were looking at parametrics, and so just to recall that we had an arc length formula before in 2 dimensions, and it was the integral from a to b of the square root of x prime of t squared plus y prime of t squared. Okay, remember that one? We had upon that along the way. So what we're going to be taking a look at now is what happens when we're looking at these vector-defined functions in terms of arc length. And then we're going to pick up on what we had sort of started a little bit in section 12.4 about talking about how sharp turns were. And in particular, it's something called curvature that we're going to be looking at. So those are our 2 topics that we're going to be looking at today. So we're going to start with theorem 12.6. And theorem 12.6 is specifically for arc length of a space curve. And it says the following. If C is a smooth curve, given by R of t equals x of t, I, plus y of t, j, plus z of t, k, on the interval AB, then the arc length of C on the interval is exactly what you would expect it to be. How do you think that we would take what we wrote at the top and adjust it given this setup? You're right. We're going to add the z prime of t squared underneath the square root. So we have our integral from a to b. It is the square root of x prime of t squared plus y prime of t squared plus z prime of t, hang on, running into each other, z prime of t squared dt. And that's actually something we've seen before. What's another way of expressing what's inside of the integral right there? Do you remember? You're right, it's the magnitude of r prime. So this is the magnitude of r prime of t. Yeah, I got it all in there. So we should find one, right? Yeah, we should definitely find one. So we're going to take a look at one. I'll switch over to the other screen after I've written a little bit of it up, just in case you're still writing a bit. We're going to compute the arc length. And our vector valued function, we're going to give it in this kind of component form right here, is 4 natural log of t, t squared, and 4t. And we're going to do the interval from 1 to 3. Okay. All right, so we're going to need derivatives. So let's actually just do that part first. What is the derivative of this vector valued function?
1 over t, 2t, 4.
Okay, everybody good with that? Okay. And then we're going to use the equation that was given in theorem 12.6. So I'll set that one up here too, and then we'll switch to another screen. So we're going to do the integral from 1 to 3 of each of these derivative components squared. So we have 4 over t squared plus 2t squared, and then plus 4 squared. Okay, so far so good? Okay, so we're going to simplify or we're going to square each of the components and then simplify the result of what's underneath that radical. So we have 16 over t squared plus 4t squared plus, 16. And the first thing that you might note is that all of them have a common factor that we can take out. So what number can we take out of all of them? 4, and it's this 4 underneath the square root, right? So we can actually pull it out of the square root as well. So that will help us a little bit in factoring this, because it will actually factor. They don't always, but this one does. So I've got a 2 that's actually outside now, and this actually was a 4 over t squared. I have a t squared, and then I have a 4. As we're attempting to look at this, recognize that oftentimes it's not possible to simplify and take square roots here and so forth and then actually take the antiderivative. And if that's the case on a particular problem, your calculator is the best thing that you can do in terms of getting an approximation. So there may in fact be those that show up where you're not able to reduce them. This one has some nice square looking components, so it sort of begs the question of, can I factor it? And Jubal's saying no, but the answer is yes. Actually, it is. I'm going to rewrite it slightly to be able to see that it's able to be factored. If I switch the locations of the t squared and the 4, it's easier to see how we can factor it. So the 2 in front, or we can put the 2 in front of the whole thing if you wish. And then I have 4 over t squared. I'm going to put my 4 in the, my 4 in the middle, and then my t squared at the end. So if I were attempting to factor this just in forms like this would be a 2 over t, and then these would be addition, of course, and then it'd have t at the end. And take a look at what happens when I multiply these together on the insides and the outsides. You see that 4 showing up in the middle? Yeah. So it's unique in the fact that it factors, because they don't often, but this one will. And so we can actually rewrite this from 1 to 3 of 2, and then it's the square root of 2 over t plus t squared, and of course the square and the square root will reduce one another. So in an effort to stay on the same page, we will just go up here. So now I have my integral from 1 to 3 of 2, and it's times 2 over t plus t. If you wish, moving that 2 back through will work. You could have left the 2 underneath the radical as a 4, and it would have factored as well. That doesn't always happen with factoring either, but it would have here. So if you had done that, you would end up at the same spot as we are now with the 2 moving back through. So this is a 4 over t plus a 2t. All right, so we're going to take the antiderivative of this now. So what's the antiderivative of 4 over t? Yeah, it's 4 natural log of the absolute value of t. Our t values actually only go between 1 and 3, which are already positive. So if you left the absolute value off in this in this particular part of the problem, you could do that and it'd be okay. And then I have t squared on the other piece, right? We're evaluating this from 3 to 0, or 0 to 3. So I have 4 natural log of 3, and then plus, oh, did I miss something? 1 to 3, thank you. Yep. Okay. 4 natural log of 3, and then I have 3 squared, and then minus 4 natural log of 1 plus the value of 1 squared, or 1. Okay, do you notice anything nice that's going to happen?
4 natural log of 1 equals 0.
Yeah, this is equal to 0. So if I combine the pieces that remain, this is 4 natural log of 3 I have 3 squared, which is 9 minus the 1, so that's 8. So it's plus 8. And if you wanted to verify that, of course, your calculator can verify it from a decimal approximation perspective. If you take the original expression that we had, even like right here, and you put in this piece of it, right, all of this into y1, you can take an antiderivative from 1 to 3. That's in math 9 in your calculator. If you're not sure what I'm talking about and you want to check in with me when we're doing board work, feel free to do so. It'll give you a decimal approximation that it won't put it in natural log form, right? And then you could do the same thing to take the 4 natural log 3 plus 8 and turn it into a decimal approximation to confirm your answer. Okay, good on arc length? Okay, so the other part of what we're looking at then today is called curvature. So let me define what that actually looks like. When we do curvature in 2 dimensions, it's relatively straightforward. It's simply what you get from the derivative. The derivative tells you how curved a curve is. It tells you how much curve there is in an equation that you have. So that doesn't work very well in 3 dimensions, so we need another form to work with. So we're going to let C be a smooth curve. And it actually is able to be done in the plane or in space. We're going to focus on doing it in space here in class today. And it's going to be given to us by we're going to do the parameter S. No, we're not. I don't know why that's different in my notes. It's 2 places, R of T. Okay. It's better anyway. Then the curvature, and K is what's used at T, is the following. So K is equal, and I'm going to give you 2 different expressions for K, and I'm going to tell you when you're most likely to want to use which one of them. Okay, they're equivalent, obviously, but we're going to be using them in different contexts. So one of them is that unit tangent, not unit, but the tangent vector, the derivative of the tangent vector. And then it's the magnitude of it, divided by the magnitude of the position vector itself. So this is one option. The second option is that K is equal to the magnitude of the cross product of the derivative of the position vector with the second derivative of the position vector divided by the position vector, derivative of the position vector's magnitude cubed. I know, it's lovely, right? They're equivalent, but they're not necessarily as equally easy to do in all circumstances. So I'd like to kind of give you some guidance on when you would want to use which one of them. This first one is actually the more convenient of the 2 to use when your T is arbitrary. What I mean by that is that we don't have a value given for T, right? T is not 4/3 or something like that. T is just T. You don't know what T is. And the second one is most convenient to use when you're given what value T is. So when T is equal to a specific number. That is a number, not a hashtag. So when T is equal to a number or a constant. And you can do either one of them in either case, and you'll get the same answer. It's just more work when we flip those descriptions and use the other one. So we're going to do an example of one when T is a number for starters. It is easier to do when T is given to you as a number. So we're going to find the curvature. And our equation for position here, R of T, is T sine 2T and then 3T. And we're going to work at T equal to 0. It's also very friendly when T is 0, right? Okay, so we're going to use the second form, the one that has the cross product, the one that has the second derivative in it and all of that. And so we need a couple derivatives. So when we take the derivative of this position vector, what do we get?
1,
Mm-hmm.
2 cos 2t, 30.
Excellent. All good? And eventually we're going to evaluate it at this particular point. So I'm just going to do that at the same time over here. What is the position vector's value when we plug in t equal to 0 for it? The 1 and the 3 are constant, so those are not going to change. What is the position vector? What is 2 cosine of 0? It's 2, yeah. So it's the vector 1, 2, 3. Let's do a second derivative. So what is the second derivative? Uh-huh. Yep. And what is the second derivative evaluated then at 0? Yeah, it's the 0 vector. So just take a stab in the dark. What do you think is going to happen when you do the cross product with the 0 vector? It's going to be 0. So this one works really nicely to do. Actually, let me write those down in pieces. Actually, no, I'll write it all. So this is the r prime of 0 cross with the r double prime of 0. So like you guys said, that's the 0 vector. Did I write it before? I wrote out more of it. That's okay. We'll write it like this. It's a 0 vector. And what's the magnitude of the 0 vector? It's 0. And while we don't necessarily need to find the denominator, let's just do it so that you can see that we did it. But if we did the denominator, so we can do it again at the value of 0, right? So the derivative at the value of 0, and then the magnitude would be the magnitude of 1 squared plus 2 squared plus 3 squared. And that would give us the square root of what? What was it, 14? 14. Mm-hmm. And then, of course, my curvature, k, is the 0 over the square root of 14, or it's just 0. So what does it mean to have curvature of 0? Could be a straight line. It's a possibility.
It's a circular curve.
It could be circular, right? It could be that it's curved in such a way. So like think about what happens in 2 dimensions when we have a derivative of 0. What are some of the things that can happen? It could be a straight line, like Annika said. What else could it be if you have a derivative of 0 in 2 dimensions?
Changes to the opposite direction.
Right, so it could be like a maximum or minimum location. Or it could even be one of those places where, like on a cubic curve, it levels out there in the middle. It doesn't actually change directions, but you still have a derivative of 0. So that's what you're thinking about in terms of a 3-dimensional space doing this too. Okay? So you've got a curvature of 0. That's totally a possibility. All right, our other one is a little messier to do because we don't have t defined. And we're going to look at the curve, same directions, just not at the given point because we're not given a point. Our r of t value is going to be 4 cosine of 2 pi t I, and we're just going to do a 2-dimensional one here, and then plus 4 sine of 2 pi, oops, that's supposed to be a t, and then j. Okay, so the curvature formula, I'll just write it on the screen since I'm missing it at this point that we're looking at on this one, is we're going to do the magnitude of t prime of t divided by the magnitude of r prime of t. And we talked about t prime of t back in section 12.4. Let me write that in here as well as a reminder. T itself is found as the position vector derivative divided by its magnitude. So these are all the components that we're going to have to put things together. And so what's the first thing I need to find? Yeah, I need to find the derivative of the position vector I'm given. So I need to find r prime of t. Okay, so r prime of t. So what's the derivative of 4 cosine of 2 pi t I?
Negative 8 pi cosine 2 pi t I.
Okay, negative 8 pi cosine 2 pi t I.
Wouldn't it be sine? No, sine.
Yes,
Yeah.
we'll fix that. Okay. Does that look good? Great. How about the second piece?
8 pi or plus 8 pi cosine 2 pi t2.
Okay, does that look good to everybody? I mean, not maybe good, but does it look correct? Okay, that's fair, isn't it? Okay, I'm going to move this over. It's too close. All right, and then what else do we need to do? We need to do the magnitude of that. Right. Now, actually, some very lovely things are going to happen as we do the magnitude here. So when we do the magnitude of this, I'm going to take each of these components and I'm going to square them and add them together. So negative 8 pi sine of 2 pi t. Okay, that's all right. And then I have positive 8 pi cosine of 2 pi t squared. Yep, I think I got all my pieces on there. So when I do this, everything becomes positive, right? So there's not going to be a negative 8 pi at the beginning of the question. They're just both going to have an 8 pi. But the 8 and the pi both get squared, but then there's a square root, and there's an 8 and a pi in both pieces. Does everybody see that? So there's a 64 pi in each of them, and then if I take the square root, it actually would be coming out as 8 pi. So much like I took the 4 out as a 2 on our first problem together, we can do the same thing with the 8 here. And that leaves me with the sine squared of 2 pi t plus the cosine squared of 2 pi t. And what is the sine squared plus the cosine squared of the same angle? It's 1, Pythagorean identity. And if I have 1 and then I take the square root, all of this sort of dissolves into simply being 8 pi. Well, that's very nice. Not only that, but then to find my t value, right, I would take the r value I started with right here, r prime rather. I'll write it out. Well, I'll copy it out. And then divide it by 8 pi, you're right. So what's going to happen, Annika? Yeah, the 8 pi's cancel. So I end up with just the sine of 2 pi t I. Yep, I'll get the negative in there. Thank you. And the cosine, that one's positive, cosine of 2 pi tj. Okay, now what? I need the derivative of that. You bet. Lots of derivatives going on. You guys just thought we weren't going to do derivatives in Calc 30. We didn't do a lot of them, but now we are. Okay, so what's the derivative of this piece? Negative sine 2 pi t I. Take a derivative. What do you have?
Negative 2 pi cos 2 pi.
Negative 2 pi cosine of t of 2t, 2 pi t, goodness, I. And then what about the next piece?
Minus 2 pi sine 2 pi.
Mm-hmm. Now what do I need? I need the magnitude of that. Lots of magnitudes today, too. And it feels like we already did it. It's quite similar, in fact, right? So when I take each of these, I have them both negative this at the moment. They're going to be squared, though. So I've got cosine 2 pi t squared plus negative 2 pi sine t 2 pi t squared. And what's going to happen?
It's gonna be 2 pi.
Yeah, it's going to be 2 pi, right? So just like the process that it simplified on the last one, if you would like to show it, feel free to. But it's just the same. It's 2 pi, right? In fact, I think, let me move that back down below so that I have more space over here. This is equal to 2 pi. So now what do I need? Or what am I supposed to do?
Divide it.
Yeah, I can find the curvature. So the curvature is to take, you know what? I'm not working with my space on my screen very well today. Let's do that. My curvature says that I'm going to take this R prime from the beginning that I got. Hang on. Where did I write it? T prime. I was grabbing the right thing and then I was grabbing the wrong thing. Okay, this piece right here. And what am I going to do with it? Oops. Wait, the magnitudes, not even the T primes. Too much zooming in and zooming out. The magnitude, 2 pi. That was the magnitude of T prime. And divide it by what?
8 pi.
8 pi. And we did all that work to arrive at the answer of 1/4. The curvature is 1/4. Lots of derivatives. Lots of opportunities to show off your good differentiation skills, right? Absolutely.
I just only want sine and cosine to show up.
Just want lots of sines and cosines.
No, only whenever.
Only
sine
sines and
squared
cosines.
plus cosine squared, it just equals 0.
Sine and
Or one.
cosine are the same angle.
Yes, correct.
They're not the same angle.
You'll see a lot of them showing up like that, so yeah. Okay, so there's a web assigned, but it's not very long. And there's the written work, which is also not terribly long. The written work is 6 problems. So we're on page 864. I take that wrong back. I think it's 7. 8. I can't count today. It's 8. Page 864, we're on problems 3, 6, 11, 14, and then 30, 33, 38, and 39. And we have over 15 minutes to start on it. So let's get started.